In this lab, we are going to synthesize alpha-bromo-p-tolic acid. This is a free radical substitution reaction. The radical reaction is initiated by ABCN. First, prepare these items and these 5 chemicals. Measure 1 milliliter of chlorobenzene and add it to a 3 milliliter conical vial. Weigh each of the 3 chemicals and add them all to the conical vial. Then, add the spin vane. Now you build the reflux apparatus using these items. Notice that the bottom tube is connected to the sink, but the top one is not. The water flows from the bottom arm of the condenser and goes away from the top arm of the condenser. You can leave the top of the condenser open. Turn on the sink carefully and you should see the water running through the condenser. To prevent splashing, just run a small amount of water. Turn on the heat and stir dials to reflux. While refluxing, you should see the solution turning yellow to a yellow-orange color, and it starts to condense down the conical vial. After 30 minutes of refluxing, turn off the heat and the stir dials and raise the apparatus to keep the conical vial away from the hot plate. Use wet paper towels to help speed up the cooling process. After it's cooled down, cap it and place it in the ice bath. Build the filtration apparatus. If you don't remember how, review the separation of a 2-component mixture lab video. Don't forget to wet the filter paper with water before starting the filtration. Take the conical vial out of the ice bath. Then, scrape the product from the spin vane and rinse it with hexane. After that, scrape the product from the conical vial onto the filter paper. Rinse the conical vial with 0.5 milliliters of hexane and add it to the apparatus. Repeat this step 2 more times. After rinsing the conical vial 3 times, remove the filter paper and transfer the solid product to a small beaker. Next, add 10 milliliters of distilled water to the beaker and stir vigorously to dissolve all the succinimide byproduct in the solution. The desired product has a very low solubility in water and would remain solid. If you see any floaties in the solution, you can stop stirring. Change the filter paper, wet the new filter paper, and add the solution of the beaker to filter the product. Rinse the beaker with 0.5 milliliters of hexane and add it to the apparatus. Repeat this step 2 more times. If you have any product left on the side of the beaker, use a spatula to scrape as much as you can from the beaker and add it to the filter paper. Weigh and record the mass of the watch glass to tare. We're going to use this mass to find the product mass later. After letting the product dry, transfer as much of it as you can to the tared watch glass. Weigh the watch glass with the product and record it. Subtract the mass of the watch glass to find out how much product you got. Obtain the melting point of the product. A-bromo-p-tolic acid has a melting point range from 228 to 230 degrees Celsius. Obtain the IR spectrum of the product as well. Now we are going to show how to calculate the percent yield. Here we have a chart of the components used in the lab. The reactants are shown in blue and the products as red. The shade in these 2 rows means you don't need to consider it in the calculation because chlorobenzene is the solvent and ABCN is the free radical initiator. As you can see in the chemical equation here, p-tolic acid and NBS are the reactants and A-bromo-p-tolic acid is the product. The mole ratio of the reactants is 1:1. When you list the amount of the components here, make sure you write down the mass you recorded, not the mass in your lab instruction. Next, calculate the moles of each compound. We use Excel, but you can also do it by hand. As you know, mole is equal to the amount divided by the molecular mass. Do the same calculation for each compound. Now we've completed the chart. Here's the equation to calculate the percent yield in the purple cell. We normally calculate percent recovery, which uses a different equation. For this lab, we need to determine the percent yield, so we'll use this equation. We have the mole of the product here, but what is the mole of the limiting reactant? If you remember from Chem 105, the limiting reactant has the smallest moles among the reactants. As you can see here, pitolic acid has smaller moles than NBS, so in this case, pitolic acid is the limiting reactant. Now you know the mole of the product and the limiting reactant. Now, since you have all you need for the calculation, you just put them into the equation. The mole of the product is this, and the mole of the limiting reactant is this. You multiply it by 100 to get the percentage. And that's how you calculate the percent yield in this lab.